You know clearly that hot staging isn't new. Soviet rockets were doing it in the 1960s. But they never made it work on a true super heavy rocket. The N-1 tried with 30 engines and never survived the first minutes of flight. Now SpaceX is attempting it with 33 engines, and even managed to catch the booster and fly it again. This isn't a repeat of history. It's the same idea pushed to a scale that once broke an entire lunar program. So what changed, and why does SpaceX think it can succeed where the N-1 couldn't? Find out everything in today's TechMap episode. April isn't just another test window. It's scheduled to be the first look at Starship Block 3, flying on Flight 12. On paper, Flight 12 looks familiar. Same suborbital path. The Super Heavy booster will light its engines for boostback and landing burns over the Gulf. The upper stage will arc across the globe and aim for a controlled splashdown in the Indian Ocean. You've seen that profile before. But this time the vehicle doing it is different. Like Flight 11, SpaceX will deploy Starlink simulator payloads and attempt in-space Raptor relights. They'll push re-entry heat shields, stress engine performance, and refine recovery techniques. Those are the visible objectives. The real story is what's changed underneath. Block 3 is built for more power, more payload, and fewer compromises on reusability. And one of the most important upgrades is a piece of hardware that most people look at the hot staging ring. The idea traces back to the Soviet N-1 rocket. Instead of separating stages and then igniting the upper stage hot staging lights, the upper engines while they're still attached to the booster. That overlap preserves velocity and reduces gravity losses during separation. It's efficient, but mechanically unforgiving. SpaceX first tested this system with a bolt-on ring. It was intentionally temporary. At the time, saving mass for landing was critical, so after stage separation, the roughly 2-ton ring was jettisoned. Dropping it made the Super Heavy lighter for boostback and ocean landing burns. A permanent structure would have penalized performance when every kilogram mattered. There was another reason to keep it removable: flexibility. Early hot staging tests revealed complex airflow and pressure behavior. Engineers needed to iterate quickly, adjusting vent sizes, internal domes, and structural details as new data came in. Issues like propellant behavior inside the booster meant nothing was locked in. A detachable ring let them swap designs flight to flight without redesigning the entire booster. And the booster itself was evolving rapidly. Keeping the ring separate avoided tearing up a vehicle that was already changing with every test. Block 3 marks the shift. After multiple flights and hard lessons, SpaceX now has enough confidence to integrate the hot staging ring directly into the booster. No more bolt-on hardware. The struts are welded into booster hardpoints. The system is now part of the structure. That brings a clear benefit: full reusability of the component. No more throwing it away mid-flight. It also adds mass. So SpaceX cut weight elsewhere. Heavier Raptor heat shielding has been reduced. Parts of the helium system have been eliminated. Dead mass was trimmed to offset the integrated structure. The new design is visually distinct: a zigzagging open strut network with larger vents that allow exhaust to escape more freely. Earlier flights, especially 7 and 8, struggled with back pressure affecting the ship's engines during hot staging. This layout directly targets that issue. Inside a protective dome shields the booster from the upper stage's exhaust plume. Frankly, those updates aren't random upgrades. They're a modern rewrite of a 1960s idea. The Soviets solved hot staging with a visible solution: a lattice-like metal framework. Crisscrossed bars let exhaust escape during separation. It worked for disposable rockets. The structure only had to survive once. SpaceX took the same principle and rebuilt it for a vehicle that's supposed to fly again and again. Instead of a flimsy add-on, Starship Block 3 fuses the structure directly into the booster's top dome. The zigzag vent pattern is built into welded struts tied to hardpoints. No loose scaffold. Think rigid bike frame, not temporary construction rigging. Why the difference? Because Starship isn't designed for a one-way mission. It has to endure 33 Raptor engines, extreme vibration, and repeated flights. Bolts and jettisoned hardware add complexity mass and long-term risk. Integration trades simplicity of replacement for durability and reuse. Separation method shows the same evolution. The N1 relied on simple clamps and pyrotechnics. The upper engines ignited amid the lower stage exhaust, and explosive bolts handled separation. For its era, that was practical. Rockets weren't meant to fly 100 times. Starship still uses clamps but avoids pyros and discarded parts. Modern flight computers allow precise timing, and the internal dome shields the booster from exhaust. That makes explosive separation unnecessary. For a reusable booster that must return to the launch site intact, avoiding debris and shock loads isn't optional. It's foundational. Even the goal has expanded. For the Soviets, hot staging helped settle propellant and improve reliability in an age without advanced computers or precision throttling. It was about making the rocket work at all. For SpaceX, hot staging also unlocks performance, roughly a 10% payload gain, while protecting engines and supporting controlled returns. The objective isn't just don't fail. It's carry more mass land precisely and repeat the process. Now look at the trade-offs. The Soviet approach was elegant in its simplicity. No extra motors. No advanced software. It supported crude missions in a harsh technological era. For the 1960s, that was enough. But N1 revealed the limits. 30 engines on the first stage created brutal vibration. Shielding and flow control weren't mature. The program suffered 4 launch failures between 1969 and 1972, each within the first 2 minutes of flight. By 1974, it was cancelled. One major constraint: the Soviets never had a test stand capable of firing all 30 engines together on the ground. Full system behavior only revealed itself in the air. SpaceX internalized that lesson. At Starbase, full Super Heavy stacks fire on massive test stands before flight. Problems surface on the ground first. It doesn't eliminate risk, but it moves discovery earlier in the timeline. More importantly, SpaceX operates under a different development philosophy. Failure isn't the end state. It's a data source. The company designs to the edge of its models, then flies into the unknown to expose what math can't predict. Early Starship prototypes proved this. SN9's crash during landing exposed propellant ingestion issues during the flip maneuver. That wasn't visible in simulations alone. It required a flight. Fixes are folded in quickly. When Flight 9 experienced a methane leak in the nose cone, gas diffusion changes were implemented before Flight 10. Iteration cycles are measured in months, not decades. That speed requires 2 things: manufacturing rate and capital. SpaceX can build the next vehicle while still analyzing the last one. Ships for Flights 8 and 9 were prepared in parallel. Heat shield tile experiments continued even as engine upgrades rolled out. Development doesn't pause for perfection. It's momentum-based engineering. And that cuts both ways. If flights fail without producing new insight, if each launch resets progress, instead of building on it, the program stalls. The stretch between Flights 7 and 9 showed how quickly confidence can wobble when results don't compound. That's the real pressure on Block 3. It isn't just about improving a Soviet-era concept. It's about proving that iteration is still generating forward motion, that each flight is adding stability instead of recycling problems. Flight 12 will look routine from a distance. Up close, it's a test of whether momentum is still on SpaceX's side. If you enjoy deep dives like this, where we go beyond headlines and actually break down the engineering hit, as so, more people see it. Drop your thoughts in the comments: Soviet design or SpaceX design? Which approach do you think wins long-term? And subscribe if you want to follow Starship's next flight step by step. Here's something most people probably don't realize. While the Soviets built their reputation on hot staging as a reliable by the late 1950s, US rockets perfected cold staging decades ago as the safer, more predictable standard. Thor Agena in 1959, Atlas Agena the same year. Even Juno 2 in 1958 experimented with different stabilization methods before liquid upper stages fully adopted ullage systems. These rockets shut down completely before separating. No overlapping flames, no engines firing through the exhaust. Instead, they used something small and subtle ullage thrusters. Here's how cold staging works. First, the booster engines shut off entirely. The stages separate cleanly using clamps or explosive bolts. No fire overlap. Now the upper stage is floating in near zero gravity. That's a problem. Liquid propellant doesn't naturally sit at the bottom of the tank. In microgravity, it drifts, so tiny thrusters fire for a few seconds. Just enough acceleration to push the fuel and oxidizer back to the bottom of their tanks. That brief push is called the ullage burn. Once the propellants are settled, the main engine ignites in stable conditions. Clean, predictable, controlled. This approach became the American standard. Saturn V used it on all 13 Apollo missions without a single staging failure. Falcon 9 still uses cold staging today, routinely and reliably. So in many ways, cold staging is safer. No engine firing into active exhaust, no intense plasma interaction between stages, less structural shock during separation, easier to manage with clustered engines. Saturn V had 5 massive F1 engines, and the system scaled cleanly, which raises the obvious question: if cold staging is so proven, why doesn't Starship use it mass? Those ullage thrusters, extra plumbing, and support systems add weight, often hundreds of kilograms per stage. On smaller rockets, that penalty is manageable. On a vehicle the size of Starship, every ton matters. Hot staging eliminates the need for ullage burns. The upper stage engines ignite, while acceleration from the booster is still present, keeping propellants settled naturally. That saves mass and preserves velocity. It's more efficient. But it demands precision. You're lighting engines inside a storm of exhaust. Venting must be perfect. Shielding must survive extreme heat. Structural loads must stay within limits. That's why the hot staging ring matters so much. It's not just a structural upgrade. It's the difference between controlled efficiency and destructive turbulence. On February 20th, just hours after NASA teams completed a full wet dress rehearsal, new data came in from the upper stage. Helium flow had stopped. This wasn't during a countdown, not during tanking. It showed up in overnight telemetry after what had been considered a clean test. And it came at the worst possible moment, right when confidence was rebuilding. Only days earlier, NASA had resolved a hydrogen leak on the core stage by replacing faulty seals. That repair restored a realistic path to a March launch. Then the helium issue surfaced. The affected system sits on the interim cryogenic propulsion stage, the upper stage that takes over after core stage separation. Its helium supply does 2 essential things. It pressurizes the liquid hydrogen and liquid oxygen tanks, and it purges engine systems to ensure clean, stable operation. If helium flow is interrupted, tank pressure cannot be maintained within the required limits. Engine conditions become unpredictable. Launch is not an option. What makes this incident difficult is that the helium system had worked in prior rehearsals. There were no warning signatures leading up to the anomaly. The interruption appeared without an obvious precursor behavior. NASA's engineering teams narrowed the investigation to a few probable areas. One possibility is a malfunctioning check valve within the vehicle. A similar failure signal appeared during the Artemis 1 mission in 2022, making this scenario technically credible. Another strong candidate is the quick disconnect umbilical interface, the physical connection between the rocket and the launch tower. That interface has historically been sensitive. Alignment, sealing, and disconnect mechanisms must perform flawlessly. Even minor irregularities can interrupt the flow. A third scenario involves a filter at the umbilical connector. This is considered less likely but remains under review. Until the root cause is confirmed, the rocket remains in a safe configuration. At the time of editing, instead of relying on onboard helium ground-based systems, we're maintaining purge capability. The next decision was logistical. The suspect components are not easily serviceable at the launch pad. Access limitations and environmental exposure complicate repairs. NASA and its contractors determined that rollback to the vehicle assembly building was the most controlled way to proceed. That rollback cancels the March launch opportunity. The earliest previous target had been March 6th. That window is now closed. Attention shifts to April. The next launch window opens April 1st. Preserving it depends on how quickly engineers isolate the fault-complete repairs and retest the affected systems. The helium leak forced a rollback. That's the event. But the bigger question isn't the valve. It isn't the umbilical. It isn't even helium itself. It's architecture. Because helium is not rare in modern rocketry. Falcon 9 uses it on every flight. And Falcon 9 flies constantly. If helium were inherently unmanageable, we would see the same pattern there. We don't. So the difference isn't the gas. It's the system built around it. Falcon 9 earned its reliability the hard way through repetition, through failure, through redesign, through flight after flight after flight. In 2015, a helium system failure destroyed the CRS-7 mission. A strut inside a composite, overwrapped pressure vessel failed. The vehicle was lost. SpaceX didn't move on quietly. They redesigned the struts, added internal liners, modified loading procedures, tightened pre-launch verification. Then they flew again. And again, and again. That cadence matters. When you launch hundreds of times, the rocket stops being theoretical. It becomes empirical. Every sensor reading builds pattern recognition. Every anomaly sharpens the model. Reliability compounds. SLS does not have that advantage. It is large, it is expensive, it flies rarely. Every launch is a major event. That means fewer real-world cycles to refine edge cases. Now look at the physical design. Falcon 9 stores helium in high-pressure composite overwrapped pressure vessels, carbon fiber tanks rated around 5,000 to 6,500 pounds per square inch. They sit inside the liquid oxygen tank. The extreme cold reduces helium volume without liquefying it. That means fewer tanks are required. Fewer tanks mean fewer lines. Fewer lines mean fewer joints. Fewer joints mean fewer leak paths. The principle is simple: remove parts. And when a rocket flies often and reuses hardware, simplicity pays twice. Fewer components reduce failure probability. Frequent reuse exposes weak points quickly. SLS operates in a very different environment. It carries enormous liquid hydrogen tanks, roughly 730,000 pounds of propellant. Liquid hydrogen is difficult. It requires continuous pressurization and careful thermal management. That drives more plumbing, more valves, more purge pathways, more interfaces between stages and boosters. Helium in SLS is not just for pressurization. It also supports purge operations, clearing unwanted gases from sensitive areas. That expands the network further. Each added function increases system depth, and depth increases exposure. SLS also relies on more traditional metallic storage configurations for helium rather than embedding composite tanks inside the cryogenic oxidizer the way Falcon 9 does. That adds structural mass and routing complexity. None of this is inherently wrong. It reflects a different design heritage, one optimized for heavy-lift hydrogen propulsion rather than high-cadence RP-1 operations. But complexity changes risk distribution. When a vehicle flies frequently, design weaknesses surface quickly and are corrected. When a vehicle flies, rarely discovery cycles stretch out. Each anomaly interrupts a long preparation campaign. Each rollback becomes significant. Now we widen the frame again. While SpaceX can now learn to manage helium through repetition, it doesn't see it as a permanent solution, because helium behaves. But it also misbehaves in very specific ways. Hydrogen leaks because it's tiny, cryogenic, and chemically reactive. Helium leaks for a different reason. It's inert, it doesn't burn, it doesn't explode, but it's extremely difficult to contain. Helium atoms are small and mobile. Under extreme compression, 5,000 pounds per square inch, and higher inside composite pressure vessels, they permeate materials. They slip through microscopic gaps in metals and composite laminations. They don't need dramatic fractures. Tiny defects are enough. Under those pressures, contained becomes a relative term. Add cryogenic temperatures into the equation, especially when pressure vessels are immersed in liquid oxygen at -183 degrees Celsius and materials contract unevenly. Carbon fiber aluminum liners, steel struts all shrinking at different rates. That mismatch matters. The 2015 Falcon 9 loss was linked to a strut inside a helium pressure vessel. The 2016 pad explosion involved a helium line rupture inside the liquid oxygen tank during fueling. Different failures. Same system stressor, extreme compression combined with extreme cold. None of that means helium is flawed. It means helium demands precision. Now apply that to SLS. When helium flow is interrupted on a vehicle the size of SLS, especially across large hydrogen tanks, scale magnifies sensitivity. A minor valve contraction from cryogenic temperatures, a trace impurity, a small obstruction on a smaller rocket that might be isolated quickly. On a massive low-cadence vehicle, every anomaly stretches into weeks of analysis. Again, not because helium is bad, because the architecture around it is complex, and this is where SpaceX made a strategic shift. When designing Starship, they removed helium entirely. Instead of carrying separate high-pressure helium tanks, Starship uses something called autogenous pressurization. The idea is direct. Use your own propellant to pressurize your tanks. Starship runs on liquid methane and liquid oxygen. The Raptor engines heat small amounts of these propellants during operation, turning a fraction into hot gas. That gas is routed back into the tanks to replace the volume of fuel being burned. No external helium system, no separate high-pressure vessels, no composite tanks are sitting inside cryogenic oxygen. As the engines run, a controlled bleed of propellant passes through hot engine components. It vaporizes. The gaseous methane flows back to pressurize the fuel tank. The gaseous oxygen flows to the oxidizer tank. As liquid leaves, gas replaces it. Pressure stays stable. The system sustains itself. From an engineering perspective, this removes an entire subsystem. No helium sourcing, no refilling of specialized gas between flights, no high-pressure composite bottles to inspect, no permeation management. For a fully reusable rocket designed to fly frequently, potentially weekly, that simplification matters. Helium is expensive. It requires logistics. It adds hardware. Autogenous pressurization uses what is already on board. That shift tells you something important. Even the company that refined helium handling through hundreds of launches chose to move beyond it when designing a next-generation system built for scale and cadence. Which brings us back to SLS. Its helium issue is specific and technical. It will likely be resolved through inspection and repair, but the broader industry trend is clear. Minimize parts. Reduce pressure extremes. Let propulsion systems support themselves where possible. Because in rocketry, every added subsystem is another place where physics can interrupt the schedule. And on a vehicle that flies, rarely, an interruption carries weight. Inside the VAB engineers are troubleshooting a helium flow problem. Across the industry, designers are asking a deeper question: how many subsystems can we remove next time? If you care about how rockets actually evolve, not just launches, but the engineering decisions behind them, subscribe and stay with TechMap. We break down the design choices, the trade-offs, and the architecture shifts that shape the future of spaceflight. If you found this valuable, leave a comment so more people can see it, and tell me in the comments, should NASA simplify SLS or double down on refining what they've built? The Artemis program is NASA's long-term mission to return humans to the Moon, to establish a continuous human presence. The goal is to develop a lunar settlement on the South Pole, a region where it's believed water ice is abundant and could be used for drinking, breathing, and as a source for rocket fuel. Artemis's long-term mission is to also lay the foundation for future crewed missions to Mars. The program is building on the legacy of the Apollo-era missions to the Moon in the late 1960s and early 70s. The Artemis program is aptly named after the ancient Greek goddess of the Moon, twin sister of Apollo.
For more than a decade now, space enthusiasts have been asking the same uncomfortable question. How did Apollo go from a blank sheet of paper to footprints on the Moon in just 8 years, while Artemis, announced in 2011, still hasn't returned a single astronaut beyond low Earth orbit? The difference begins with urgency. At its peak, Apollo consumed 4.4% of the U.S. federal budget. Fueled by Cold War rivalry and national prestige, Congress opened the funding floodgates. Speed was the mission. Artemis operates in a different era. NASA now receives a fraction of that support, constrained by political gridlock and competing priorities. Instead of a tightly integrated program, Artemis has evolved into a sprawling network of contractors across 29 states, slower, more complex, and structurally heavier. The hardware reflects that reality. SLS repurposes Space Shuttle-era technology, requiring costly modernization. Orion has faced delays of its own, but funding and legacy systems are only part of the problem. The deeper challenge is architectural complexity. Unlike Apollo's unified design, Artemis depends on multiple giants: Boeing's SLS, Lockheed's Orion, SpaceX's Starship lander, and Blue Origin's alternative, all required to operate in perfect sequence. Nowhere was this risk clearer than in the original Artemis III plan, which attempted 3 firsts at once: a crewed Starship flight, large-scale orbital refueling, and a lunar landing. Any one would be ambitious. Together, they turned the mission into a gamble. Starship's refueling system remains unproven at scale. Multi-company docking adds risk. One leak, one glitch, one failure in the chain, and as delays mounted, headlines shifted from anticipation to concern, especially as China's lunar ambitions accelerated. The question is no longer just when America returns to the moon. It's whether it can do so fast enough. That mounting pressure forced a rethink, and that rethink began with Artemis III. The timeline of 2027 remains, but the mission itself has changed dramatically. Instead of attempting a lunar landing on its first try, Artemis III will now serve as a proving ground in low Earth orbit. The human landing system will launch uncrewed and rendezvous with a crewed Orion capsule. Rather than a one-shot moon attempt, the mission will focus on docking demonstrations, systems validation, and operational rehearsals. It is no longer SpaceX's solo performance. Astronauts will evaluate lander systems from multiple partners, whether SpaceX's Starship, Blue Origin's Blue Moon, or potentially both. Inside Orion, the crew will also test next-generation lunar spacesuits in the vacuum of space. If this sounds familiar, it should. In 1969, Apollo 9 tested the lunar module in Earth orbit before committing to a lunar landing. It was a dress rehearsal, a controlled environment to uncover flaws before the stakes became existential. Artemis III now mirrors that philosophy. Rather than betting everything on an unproven stack, NASA is decomposing the risk. Learn in orbit. Validate systems. Identify weaknesses. Then proceed. The actual lunar landing has shifted to Artemis IV, currently targeted for 2028. And notably, the specific lander for that mission has not yet been finalized. Performance during Artemis III will play a decisive role in determining which system earns the responsibility of carrying astronauts down to the lunar surface. Quietly, beneath the official press releases and congressional hearings, a different kind of race is unfolding. On one side stands Elon Musk's SpaceX, with its towering Starship HLS. On the other, Jeff Bezos's Blue Origin, developing the Blue Moon Mark II. Both are competing for the same prize: to carry American astronauts back to the lunar surface. For the space community, Starship HLS needs little introduction. It is colossal. Standing over 50 meters tall with a 9-meter diameter, it dwarfs Apollo's lunar module. It runs on methane-fueled Raptor engines, a propellant choice designed for reusability and future Mars missions. And on paper, it is staggering. More than 100 tons of payload capacity to the lunar surface, enough for crews of 4, habitats, rovers, and the beginnings of a permanent base. Blue Origin's Blue Moon Mark II takes a very different approach. At roughly 15 meters tall, it is far more compact, narrower, more specialized. Its payload capacity is closer to 20 tons, about 1/5 of Starship's. That might sound like a disadvantage, but it reflects a different philosophy. Mark II isn't designed to brute force a lunar base into existence. It is optimized for precision operations and gateway docking. Instead of methane, it uses hydrogen-oxygen BE-7 engines. 2 landers. 2 radically different visions of how to return to the moon. But the real contrast appears not on the surface, it appears in orbit. Starship requires orbital refueling. After launch, it must be topped off by a fleet of dedicated tanker starships in low Earth orbit before heading toward the moon. Estimates suggest anywhere from 10 to 20 tanker flights may be required to transfer more than 1,200 tons of super-cold methyl-ox propellant. Blue Origin's solution is arguably even more elaborate. Instead of tanker versions of the same vehicle, Blue Moon relies on something called the cislunar transporter. It consists of 2 major components: a tug equipped with 3 BE-7 engines and a tanker module for carrying propellant. These pieces launch separately aboard New Glenn rockets and assemble in Earth orbit, snapping together like orbital Lego bricks. Then it gets more intricate. Additional New Glenn rockets launch upper stages carrying residual propellant. The assembled transporter docks with those stages and siphons off their leftover fuel. Once filled, it travels to a near-rectilinear halo orbit around the Moon, the same orbit planned for the Gateway Station, where it refuels the Blue Moon lander. Compared to Starship's direct tanker-to-lander approach, Blue Origin's method requires more launches and more assembly steps. Starship makes everything simple, but simplicity does not mean easy. Starship's greatest strength, its sheer size, is also its greatest engineering burden. Moving over 1,000 tons of cryogenic methane and oxygen in orbit has never been demonstrated at this scale. Methane, while easier to handle than hydrogen in some respects, still presents boil-off challenges. Raptor engines must remain stable after long-duration cryogenic exposure. Docking systems must operate repeatedly without failure. And then there's Starship Block 3, the variant expected to support Artemis. As of now, it has not flown. That means many of the systems required for Artemis remain untested in real mission conditions. With Artemis 3 targeting 2027, time is measurable. That reality has placed enormous pressure on SpaceX teams in Texas and California. But paradoxically, NASA's recent restructuring of Artemis 3 may have given them breathing room. Under the revised plan, the most daunting challenge, large-scale orbital refueling for a lunar mission, is temporarily removed from the critical path. The LEO demonstration can be achieved with far fewer launches, no lunar descent engines, no landing legs, no surface operations. Just the fundamentals: life support, docking, crew safety. That said, few expect SpaceX to sit idle. A ship-to-ship propellant transfer demo in late 2026 would align perfectly with their philosophy. They need data. They need failure points. They need iteration cycles, because that is how SpaceX operates. In late 2025, the company formally proposed what it called a simplified mission architecture to NASA. The recent Artemis redesign strongly resembles that proposal. It allows SpaceX to focus on what it already does well: rapid prototyping, frequent launches, and iterative testing in low Earth orbit before tackling the uniquely hostile conditions of the lunar South Pole. This aligns with Musk's core engineering mantra: test to failure. SpaceX does not aim for flawless first attempts. It flies early, breaks things, fixes them, flies again. Apollo, in many ways, followed a similar incremental ladder of missions, each building toward the next. A restructured Artemis III gives Starship something it desperately needs: the chance to prove itself in stages rather than all at once. Not perfection or bust, but progress through iteration. So how close is SpaceX to being ready? Closer than it may seem. Behind the spectacle of test flights, SpaceX has been steadily clearing critical milestones for Starship HLS. In February 2024, the company completed full testing of its environmental control and life support system, the hardware that will keep astronauts alive. That same month, NASA validated full-scale docking tests between Starship HLS and Orion, later extending to gateway configurations. More than 30 Artemis-specific milestones have now been completed, spanning power, communications, propulsion, navigation, and space environment protection. Then came a key breakthrough on March 14, 2024. During Integrated Flight Test 3, SpaceX successfully demonstrated in-flight cryogenic propellant transfer inside Starship, an essential precursor to the far more complex orbital refueling campaigns required for a lunar mission. Now attention shifts to Block 3, the configuration expected to carry the Artemis burden. SpaceX is targeting its debut around Flight 12, currently tracking toward March. Hardware preparation is already underway. Ship 39 and Booster 19 are leading that charge. On February 26th, after months inside Mega Bay 2, Ship 39 rolled out, notably without engines, to undergo cryogenic proof testing. Upcoming tests will go further: forward and aft flap validation, structural squeeze tests using chopstick simulators, replicating the mechanical loads from the launch tower arms that catch returning boosters. Every interface, every stress point is being pushed deliberately. Once complete, Ship 39 will return to the production site for engine installation before rolling back out for static fire testing. Only then does it approach flight readiness. Meanwhile, Booster 19 has already completed a rigorous pre-flight test campaign. Multiple full cryogenic proof cycles were conducted, a direct response to issues that led to the loss of Booster 18. The lessons learned were not theoretical, they were structural.
The decision isn't ideological, it's structural. Congress won't allow NASA to skip the moon. Testimony from 2024 made this explicit. Lawmakers view lunar return as essential to American space leadership, particularly with China establishing its own permanent base. Trump's first space policy directive during his initial term prioritized the moon. That hasn't changed. Meanwhile, SpaceX has the funding and capability to reach Mars regardless of government plans. Starlink's projected 2025 revenue of $10 to $11.8 billion comes remarkably close to matching NASA's entire human spaceflight budget, around $12 billion for Artemis 1 SS operations and exploration systems. This highlights how private revenue now rivals government funding to power Moon and Mars ambitions. The company doesn't need permission to send cargo to Mars, just a launch license. If NASA chooses not to participate, SpaceX will partner with other countries instead. This creates an impossible position for policymakers. Standing aside while a private company leads humanity to Mars undermines the entire justification for NASA's existence. Blocking SpaceX serves no strategic purpose and damages American credibility. The solution is simultaneous pursuit. SpaceX commits to lunar missions through NASA contracts. NASA partners with SpaceX for Mars. Both destinations move forward. SpaceX's lunar role is already defined. The company holds the contract for Artemis III, the first crewed landing since 1972. The mission requires a specialized variant called Starship HLS, Human Landing System. In October, NASA Acting Administrator Sean Duffy announced that Artemis III would be opened to competition. Musk responded immediately. Starship will end up doing the whole moon mission, mark my words. That statement wasn't about a single flight. It signals intent to dominate the broader Artemis program. Musk has referenced Moonbase Alpha multiple times, suggesting permanent infrastructure rather than brief visits. The timeline is tight. Artemis 3 is currently scheduled for mid to late 2027, though delays are probable. Before that mission can proceed, SpaceX must demonstrate several foundational capabilities: orbital refueling, controlled landing, and full vehicle reuse. These milestones are planned for 2026. Refueling matters more than most technical challenges. Starship burns nearly all its propellant to reach orbit. Reaching the Moon requires multiple tanker flights to fill a depot in low Earth orbit, then transferring fuel to the lunar-bound vehicle. SpaceX targets a refueling demonstration by mid-2026. The system's architecture is unusual. Unlike Apollo, which used a small lander, Starship HLS is massive, capable of delivering 100 tons to the lunar surface per flight. That capacity changes what's possible. Infrastructure can arrive in single shipments rather than assembled piece by piece over the years. SpaceX President Gwynne Shotwell has backed Musk's lunar commitments publicly. In an industry where executives often hedge, her support carries weight. Shotwell is known for delivering on schedules others consider impossible. The Moon offers immediate advantages. Water ice exists at the poles. Access to that water eliminates the need for constant resupply from Earth. It also enables fuel production water splits into hydrogen and oxygen, both propellants. But the Moon's strategic value isn't just resources, it's proximity. Launch windows to the Moon open continuously. Travel time is 3 days. If something fails, crews can return quickly. Mars offers none of these safety margins. For that reason, Moon could serve as an ideal testbed for Mars exploration, offering a nearby proving ground for Starship technologies and operations. Musk's Mars timeline has been public for years, but recent updates sharpened the specifics. The first uncrewed cargo mission is targeted for late 2026. That launch window opens in November and stays viable for several weeks. The payload includes Optimus robots designed to test autonomous surface operations. Musk has acknowledged this timeline could slip into 2027, given technical complexity. If the 2026 mission succeeds, SpaceX will use the 2029 window to send additional cargo. Launch opportunities to Mars occur roughly every 26 months, determined by orbital alignment between Earth and Mars. Missing a window delays everything by 2 years. Crewed missions follow cargo, not the reverse. Musk's current estimate places the first human landing between 2029 and 2031. That timeline assumes multiple successful cargo deliveries first. SpaceX won't risk lives until substantial supplies and redundant equipment are already on the surface. Mars presents challenges the Moon doesn't. Distance is the obvious one. Travel time is 6 to 9 months, depending on trajectory. But the environment is harsher. The atmosphere is 1% as dense as Earth's, offering no protection from radiation. Temperatures at the equator can reach 70 degrees Fahrenheit during summer days, but plunge far below freezing at night. Water is the critical unknown. Mars has polar ice caps, but those regions are extremely cold and logistically difficult. If substantial underground water reserves exist elsewhere, they haven't been confirmed. Without accessible water, early settlements face severe limitations. Yet Mars has strategic advantages that justify the risk. The planet likely formed around the same time as Earth. NASA's Perseverance rover recently found rock formations suggesting Mars once had liquid water and possibly life. Whether that life existed is still uncertain, but the planet's history makes it scientifically invaluable. Mars also provides space. The planet is smaller than Earth, but it has no oceans. Nearly the entire surface is available for development. That's roughly the same land area as Earth's continents combined. Gravity on Mars is 38% of Earth's, stronger than the Moon's 16%, but weak enough to reduce energy costs for construction and transport. Launching from Mars requires far less fuel than launching from Earth, which matters for future missions deeper into the solar system. Most importantly, Mars enables fuel production. The atmosphere is 95% carbon dioxide. If water is present, chemical reactions can produce methane and oxygen, the exact propellants Starship uses. This eliminates the need to transport all fuel from Earth, making return trips and extended exploration feasible. Musk's vision for Mars isn't a research outpost. It's full colonization targeting a self-sustaining city of 1 million people. During each 26-month Earth-Mars launch window, SpaceX aims for thousands of Starship flights from a mature fleet, potentially delivering hundreds of thousands of tons of cargo to the Mars surface to build infrastructure. A self-sufficient Mars city requires roughly 1 million tons of material total. At scale, with 100 to 150 tons delivered per Starship landing, this becomes feasible across 4 to 5 launch windows, 8 to 10 years, assuming rapid reuse and high success rates. Realistically, with development delays, we've seen a permanent settlement remains possible within 2 decades. Managing both destinations simultaneously requires careful sequencing. From late 2026 through 2028, the Moon takes priority. NASA contracts drive this focus, but competition with China also matters. Beijing has outlined clear plans for lunar infrastructure, and allowing another nation to dominate the Moon would be politically unacceptable to Washington. During this period, Mars remains a parallel effort, but with less urgency. SpaceX will attempt cargo landings if the 2026 window is viable, but lunar commitments come first. As the decade progresses, priorities will shift. By 2029, assuming Artemis missions succeed and lunar infrastructure is established, Mars will demand increasing attention. The 2029 and 2031 windows represent SpaceX's best opportunities for crewed landings. Both programs depend on the same core infrastructure. Starship is the vehicle for both destinations. Orbital refueling must work for either mission. The manufacturing base at Starbase Texas and Florida's launch facilities serve both efforts. Fleet scaling is the bottleneck. Sustained operations on the Moon or Mars require dozens of Starship's vehicles for crew, cargo refueling tankers, and specialized variants like HLS. SpaceX is already expanding production capacity, but building that fleet takes time. The company is also developing shared surface systems. Habitat's life support power generation and communication infrastructure will be largely identical between locations. This commonality reduces development costs and accelerates deployment. Refueling remains the highest risk dependency. Without reliable propellant transfer in orbit, neither destination is accessible at scale. SpaceX has compared the challenge to aerial refueling for aircraft, difficult initially, but routine once mastered. The mid-2026 demonstration will reveal whether that confidence is justified. SpaceX's dual strategy forces a recalculation of what's possible in space exploration. For decades, human spaceflight has been incremental. Programs lasted years and cost billions to achieve modest objectives. The International Space Station took 13 years to assemble and requires constant resupply. Artemis 1, an uncrewed test flight, cost over $4 billion. SpaceX is collapsing those timelines and costs. Starship's full reusability means launch costs could drop to a few $1,000,000 per flight. At that price point, mistakes become affordable. Missions can fail without ending programs. This changes the competitive landscape. China is pursuing lunar and Mars missions with state backing. Blue Origin is developing its own heavy lift system. Both organizations now face a competitor that moves faster and spends less. International partnerships are shifting as well. If SpaceX reaches Mars, first other nations will seek participation through the company rather than through NASA. That dynamic undermines traditional space diplomacy, where governments coordinated through agencies. The economic implications are unclear, but potentially significant. If the Moon becomes accessible at a commercial scale, industries will follow. Resource extraction, manufacturing in low gravity, and tourism are all plausible. Mars is further out, but a permanent settlement would create demand for goods and services across the supply chain. The ultimate question isn't technical. It's whether humanity wants to remain confined to one planet. Musk believes the answer is no. His public statements emphasize existential risk asteroid impacts, supervolcanoes, nuclear war. Spreading across multiple worlds reduces the chance of extinction. That argument resonates with some and strikes others as alarmist, but it's no longer hypothetical. The hardware exists. The timelines are set. Success is uncertain, but the attempt is already underway. SpaceX isn't asking for permission, it's presenting results. The dual strategy makes those results inevitable for both destinations, not just one. The Moon will see permanent infrastructure by 2030. Mars will receive cargo by 2027, and possibly humans by 2031. Both timelines could slip, but both are moving forward. The surface story is straightforward enough. Starship version 4 upgrades the upper stage from 6 engines to 9, specifically adding 3 more Raptor vacuum engines to the existing configuration of 3 sea-level and 3 vacuum engines. That brings the ship's vacuum engine count to 6, arranged in a hexagonal pattern around the 3 central sea-level Raptors used for landing and atmospheric control. Combined with Super Heavy's 33 Raptors, that's 42 total. The meme number. The cosmic joke. And yes, it's real engineering too. More vacuum engines mean better efficiency in space, higher thrust where it matters most, engine redundancy if something fails, fewer tanker flights needed for orbital refueling, currently 8 to 10 launches just to fuel one Mars-bound Starship. On paper, Starship version 4 is enormous. Nearly 150 meters tall, it stands roughly 3 Statues of Liberty stacked end to end. The Super Heavy booster alone stretches to about 81 meters, its propellant tanks lengthened to carry far more fuel, while the upper stage reaches roughly 61 meters in height. The crewed version 4 variant will also feature more than 1,000 cubic meters of pressurized volume, about 10% more than the entire International Space Station. That's not a statistic you can just gloss over. More internal volume than the ISS contained within a single vehicle. That space translates directly into survivability. Room for proper crew quarters, dedicated work areas, exercise equipment, medical facilities, and long-term storage for food tools and spare parts. On missions lasting months, cramped living conditions aren't just uncomfortable, they're a real psychological risk. Version 4's expanded interior is designed to reduce that strain, helping crews stay healthy, focused, and functional all the way to Mars. Performance scales with size. Starship version 4 is designed to deliver more than 200 tons to low Earth orbit in fully reusable mode, roughly double what Block 2 was originally expected to achieve. At liftoff, the booster will produce close to 10,000 tons of thrust using Raptor 4 engines. The timeline points to 2027. The vision is Mars. From the outside, this looks like exactly what SpaceX promised: bigger, more powerful, closer to making interplanetary travel sustainable. But here's the question no one's asking. If the current design works, why does SpaceX need to add 50% more vacuum engines and stretch the entire vehicle? The answer isn't in the press releases. It's in the dry mass. Dry mass is what the rocket weighs when empty structure engines heat, shields, tanks, plumbing, everything except fuel. And for Starship, dry mass has been growing in the wrong direction since day one. Back in 2018 and 2019, SpaceX's presentations showed dry mass targets for the upper stage around 85 to 120 metric tons. That was the goal, light efficient, built for rapid reusability. The Mark 1 prototype hit closer to 200 tons. Block 1 came in around 149 tons. Still heavy, but progress. Block 2, 161 tons, and rising. Every iteration added weight. Enhanced heat shielding after tiles failed during re-entry. Fire suppression systems after engine bay fires. Armor around the engines. RCS thrusters for better control. Structural reinforcements for the stretched tanks. Each addition made sense on its own. Each one made the vehicle safer, more reliable, and more capable of surviving the stresses of launch and re-entry, but they also made it heavier. And in rocketry, every kilogram of dry mass is a kilogram you can't use for payload. Here's where the numbers get uncomfortable. SpaceX's early targets for Block 1 and Block 2 aimed for 100 to 150 tons, to low Earth orbit in fully reusable mode. That was the promise. That's what Starship was sold on: high, payload, low-cost, rapid reuse. The reality, based on flight data and design updates, is closer to 35 to 100 tons. Excess dry mass didn't just nibble at the margins, it eroded payload capacity by roughly 50 to 100 tons total. A heavier structure means you need more propellant just to reach orbit. More propellant means heavier tanks and stronger plumbing. The rocket burns more fuel lifting itself, leaving less performance for the mission. SpaceX is delivering half or less of what was promised, and this isn't a temporary setback, it's structural. At this point, it's fair to say the issue isn't slow development, it's a design trap SpaceX walked into and hasn't found a way out of. So what does SpaceX do when the rocket is too heavy? Make it bigger. That's what version 4 is. Starship version 4 stretches the upper stage to 61 meters. The booster grows to 81 meters. Propellant capacity increases to 4,050 tons in the booster and 2,300 tons in the ship. The engine count jumps from 39 to 42. More fuel, more engines, more thrust, more structure. The logic is simple: if you can't reduce the dry mass, add enough power and propellant to compensate for it. On the surface, that works. Version 4's projected payload of over 200 tons to low Earth orbit sounds transformative. It would cut refueling flights. It would enable heavy cargo pre-deployment to Mars. It would make Artemis HLS requirements feasible without excessive tanker launches. But look closer. A longer vehicle doesn't just mean more fuel. It means more structural mass. Bigger tanks need thicker walls. More engines need heavier mounts and plumbing. The stretched upper stage requires reinforced load paths to handle the stress of 6 vacuum engines firing simultaneously during hot staging. You're adding mass to solve a mass problem. The strategy isn't mass reduction. It's scale and power. SpaceX is building a bigger rocket to carry the weight of everything that went wrong with the smaller one. And that's not how rockets are supposed to evolve. Consider Saturn V. The entire stack, first stage, second stage, third stage Apollo spacecraft had a dry mass of around 310 tons. It delivered 140 tons to low Earth orbit. Starship Block 2's upper stage alone weighs 161 plus tons dry, and it delivers 35 to 100 tons of reusable. You're carrying more dry mass to deliver less payload. The efficiency ratio is inverted. Version 4 tries to fix this by brute force: 42 engines, 10,000 tons of thrust-stretched tanks. The rocket gets more capable on paper while becoming less practical in reality, because every ton of dry mass is a ton that doesn't go to Mars, and refueling becomes exponentially harder when the vehicle itself is the problem. Here's what SpaceX won't say out loud. Version 4 is designed to land on Mars, but whether it's economically viable for sustained Mars operations depends entirely on flight testing in 2027 validating SpaceX's performance projections. If dry mass continues growing, or Raptor 4 underperforms, version 4 might prove the concept without solving the economics. And that would mean SpaceX is still 1 or 2 iterations away from the actual Mars vehicle. There's no guarantee, and the path to get there reveals a troubling pattern. SpaceX broke the development roadmap into stages: version 2, then version 3, then version 4. Specifically to avoid changing too many things at once. That sounds reasonable. Incremental progress, manage risk. But this is exactly the approach that trapped SLS. Incremental changes that preserve inherited problems. Each version adds complexity to solve the issues created by the last version. Technical debt compounding across iterations. The difference is that SpaceX moves faster, but speed doesn't fix architecture. And version 4's architecture comes with costs NASA's SLS never had to face. Version 4 won't fit in SpaceX's existing assembly bays. The vehicle is too tall. So before SpaceX can build version 4, it has to build the Gigabay, a massive new facility at Starbase capable of stacking a 150-meter rocket. That means building the building before building the rocket. Fixed infrastructure costs are rising before payload capacity improves. Then there's the engine. Everything, every performance claim, every payload projection, Every refueling calculation depends on Raptor 4 delivering roughly 300 to 330 tons of thrust per engine. That's an 18% jump over Raptor 3. Without it, as one source bluntly put it, Starship would simply be a more complex rocket than Falcon Heavy rather than a revolution. No margin for error. Single point of failure in the entire architecture. If Raptor 4 underperforms, Starship version 4 underperforms. If Starship version 4 underperforms, Mars slips further away, and the dry mass problem. Still there, still growing. Flight data from 2027 will tell the story SpaceX can't yet write, whether adding 30% more engines actually closes the gap or just moves the goalpost. Here's what I want to know. If you were running SpaceX and saw these dry mass numbers, would you double down on version 4, or would you start designing a completely different architecture from scratch? There's no obvious right answer here. Comment what you do and why. And if you're tired of surface-level space coverage that just repeats what Elon tweets, subscribe. This channel digs into what the engineering actually means. So what does 42 engines really mean? It's not the answer to life, the universe, and everything. It's evidence of the question SpaceX is still trying to solve. Can you fix a rocket's mass problem by making it bigger? The 42nd engine isn't there because the design is optimal. It's there because the design is heavy. Version 4 had to add 6 vacuum engines, 50% more than Block 2, just to overcome the structural weight the vehicle shouldn't have gained in the first place. The prophecy isn't about reaching for the stars. It's about what made reaching necessary. And that story is still being written. For years, ULA had a reputation that was almost untouchable. They were the orchestra of precision in the launch industry, not the cheapest ticket in town, but if you bought one, you knew the show would go on flawlessly. Their unofficial slogan might as well have been, "Yes, we're expensive. No, we don't fail." And honestly, they backed it up. The Atlas V became the gold standard of reliability. Since its debut in 2002, it has flown 106 missions. 106 successes. 0 failures. In the rocket world, that's legendary status. A big part of that story wasn't just ULA, it was Northrop Grumman's solid rocket boosters, especially the GEM-63 series. These beasts deliver 375,000 pounds of thrust each for 94 seconds, strapping raw explosive power onto the side of Atlas V. And their track record, over 1,000 motors have been flown across 132 Delta II launches. No failures. That's not luck. That's generational reliability. But spaceflight doesn't stand still. When ULA introduced its next-generation rocket Vulcan Centaur, it came with an upgraded booster, the GEM-63XL longer. More powerful. Built to push Vulcan into the future of national security and commercial missions. Vulcan's debut flight was smooth. Confidence remained high. Then came October 4th, 2024, Vulcan's second flight. About 30 seconds after liftoff, something looked off. Sparks flickered. The exhaust plume changed color. Then it appeared that part of a booster nozzle had come apart. Here's what actually happened. One of the GEM-63XL boosters suffered a burn-through near its nozzle throat. The internal protective liner failed, letting extreme heat damage the structure. The booster lost thrust early, and its separation was delayed by about 20 to 30 seconds. But there was no explosion. Vulcan's core stage BE-4 engines immediately compensated gimbaling to keep the rocket stable and on trajectory. The mission still succeeded. From the outside, it looked like impressive resilience. Behind the scenes, it triggered serious concern. Investigators traced the issue to a carbon composite insulator liner inside the nozzle. Think of it as a heat shield for the hottest part of the motor. That liner melted. The root cause: a manufacturing defect specifically related to bonding and glue processes during production. ULA and Northrop Grumman reviewed the build process, strengthened the liner bonding, and conducted a full-scale ground test in February 2025. The fix appeared to work. Vulcan was cleared to fly again. The third mission: flawless. Problem solved. Right, not quite. On the fourth flight, USSF-87 in February 2026, flames appeared again around the same 20 to 30 second mark. Same phase of flight, same type of booster, another GEM-63XL anomaly. And that's when the space community started asking serious questions. What's really going on? There are now two major hypotheses. Hypothesis 1. The manufacturing defect was never truly fixed. The leading theory is simple and uncomfortable. The original flaw may still exist somewhere in the supply chain. Even if corrective actions were implemented, subtle process inconsistencies could still be producing defective insulator liners. Composite materials are complex. Manufacturing tolerances matter enormously. A slight variation in bonding pressure, curing temperature, or material layering could reintroduce the same weakness. If that's the case, this isn't a design flaw, it's a quality control problem. And those are notoriously difficult to eliminate completely. Hypothesis 2. This is a different problem entirely. Even though the symptoms look similar, experts aren't ruling out a new issue. The GEM-63XL is a stretched, uprated version of a proven design. But scaling up a solid rocket motor isn't trivial. Thermal loads change, structural stresses change, flow dynamics shift. It's possible there's a deeper design interaction that only appears under specific flight conditions, something not caught in ground testing. If that's true, then this could point to a more systemic engineering challenge rather than just manufacturing variants. As of now, there's no official statement from ULA directly addressing or dismissing the questions surrounding the second GEM-63XL anomaly. And let's be real, when the same part fails twice in 4 flights, that's not a yellow flag. That's a code red. This is happening at a particularly sensitive moment. The Pentagon was already frustrated. Vulcan development ran late. Certification took longer than expected. That pushed critical national security launches into limbo. ULA originally won about 60% of the NSSL Phase 2 contract, roughly 48 to 60 missions between 2022 and 2027. But because Vulcan wasn't certified on time, more than 20 missions sat waiting. Some had to be reassigned to Atlas V. Others went to SpaceX's Falcon 9. By the time Vulcan was finally certified after USSF 106 in August 2025, only 2 operational military missions had flown on the new rocket. Meanwhile, around 15 to 20 missions were stacked up in backlog for 2026 and beyond. And 2026 was supposed to be the big comeback year. ULA projected 18 to 22 Vulcan launches in 2026. More than half over a dozen were military missions. They needed to hit a cadence of roughly 2 launches per month to clear the backlog and restore confidence. And USSF-87 in February 2026 was the starting gun. The booster anomaly on February 12, 2026, changed everything. Even though the rocket survived again, the optics are brutal. Space Force immediately halted Vulcan missions pending investigation. And here's the key difference this time. After the first anomaly in 2024, ULA spent about 5 months investigating adjusting manufacturing processes and concluding the boosters in inventory were safe to fly. That fix didn't hold. Now, after a second, strikingly similar failure, the scrutiny will be on another level. Military officials have openly signaled they're not eager to test Vulcan's ability to compensate for another dramatic booster issue. Yes, the rocket can survive a failed solid rocket booster. But national security payloads are not experimental test articles. You don't gamble billion-dollar missile-warning satellites on the core can handle it. This time they might expect a triple check, much more careful. And that takes time. If the first anomaly required 5 months, the second could easily demand longer. A return to flight no earlier than late 2026 might be optimistic. It would not be shocking if Vulcan doesn't fly back this year at all. So here is the billion-dollar question for you. Best case A, thorough investigation, confirmed root cause, validated fix, late 2026 return. More conservative view, 2027. Do you think Vulcan returns this year, or does this booster issue ground it well into next year? Drop your thoughts in the comments below. Of course, this isn't just about ULA's backlog getting longer. It's about something far bigger losing ground permanently to SpaceX. And right now, that risk is higher than at any point in the last decade. How SpaceX took the lead, quietly then completely. If you zoom out, the shift didn't happen overnight. It took about 13 years. In 2012, Falcon 9 started earning Pentagon trust through ISS cargo missions. Nothing flashy, just steady performance. In 2019, Falcon Heavy launched classified National Reconnaissance Office payloads. That was a signal SpaceX was no longer the new guy. Then came a turning point. When sanctions complicated ULA's access to Russian RD-180 engines for Atlas V, the Pentagon hedged its bets. In 2020, SpaceX won roughly 40% of the NSSL Phase 2 missions, about 80 to 100 launches planned through 2027. That hedge became a shift. Between 2020 and 2023, SpaceX stacked up successful launches at scale. Dozens turned into hundreds. Costs dropped 50 to 70% compared to legacy pricing. Reliability held. By 2023, SpaceX wasn't just competing, it was leading. More than 60% of military missions, including GPS-3 and high-value NRO payloads, went to Falcon 9 or Falcon Heavy. And here's where timing matters. From 2023 to 2025, as SpaceX surged past 65% market share, Vulcan kept slipping. Certification delays stretched on. At least 24 missions were reassigned from Vulcan to SpaceX. By the time Vulcan was certified in August 2025, SpaceX was flying roughly 70% of U.S. Space Force launches annually. That's dominance. Now add a grounded Vulcan in 2026. You can see where this goes. At first glance, one highly capable launch provider sounds efficient, but in national defense, dominance is not the same thing as resilience. The U.S. military does not want one primary door to space. It wants at least two. Even if SpaceX is fast, and they are, they cannot absorb every mission overnight. Launch pads are finite. Integration facilities are finite. Range availability is finite. Trained crews are finite. If Vulcan is sidelined for months, satellites don't instantly move to Falcon 9. They wait. And when satellites wait, capability waits. Almost everything waits. In a world of rising global tension, delay is not neutral. It's risk. Here is the satellite problem no one talks about. Not every military satellite can simply switch rockets. Some are dual compatible, many are not. GPS satellites are generally flexible, but certain missile warning satellites worth billions collectively are tightly integrated around specific performance envelopes. Requalifying a satellite for a different launch vehicle is not like changing airlines. It can require structural analysis, vibration, retesting payload, adapter redesign software adjustments, and months of paperwork. Last but certainly not least, it's the strategic risk of one dominant provider. If ULA weakens too much, or if Vulcan loses trust, the Pentagon loses leverage. Competition keeps pricing disciplined forces, schedule performance, and drives innovation. Without it, negotiation power shrinks. And there's another layer. What happens if Falcon 9 has a fleet-wide issue? Groundings happen in rocketry. Even the most reliable vehicles face anomalies. If the U.S. depends overwhelmingly on one system, a single technical problem can freeze national security launches.